in nuclear physics and nuclear chemistry. The nuclear shell model is a model of the atomic nucleus which uses the Pauli exclusion principle to describe the structure of the nucleus in terms of energy levels. The first shell model was proposed by Dmitry Ivanenko in 1932. The model was developed in 1949 following independent work by several physicists, most notably Eugene Paul Wiener, Maria Goeppert-Mayer and J. Hans D. Jensen, who shared the 1963 Nobel Prize in Physics for their contributions. The shell model is partly analogous to the atomic shell model, which describes the arrangement of electrons in an atom, in that a filled shell results in greater stability. When adding nucleons to a nucleus, there are certain points where the binding energy of the next nucleon is significantly less than the last one. This observation, that there are certain magic numbers of nucleons, 2, 8, 20, 28, 50, 82, 126, which are more tightly bound than the next higher number, is the origin of the shell model. The shells for protons and for neutrons are independent of each other. Therefore, one can have magic nuclei, where one nucleon type or the other is at a magic number, and doubly magic nuclei, where both are. Due to some variations in orbital filling, the upper magic numbers are 126 and, speculatively, 184 for neutrons but only 114 for protons, playing a role in the search for the so-called island of stability. Some semi-magic numbers have been found, notably Z equals 40, giving nuclear shell filling for the various elements. The 16th of may also be a magic number. In order to get these numbers, the nuclear shell model starts from an average potential with a shape something between the square well and the harmonic oscillator. To this potential a spin-orbit term is added. Even so, the total perturbation does not coincide with experiment, and an empirical spin-orbit coupling, named the Nielsen term, must be added with at least 2 or 3 different values of its coupling constant, depending on the nuclei being studied. Nevertheless, the magic numbers of nucleons, as well as other properties, can be arrived at by approximating the model with a 3-dimensional harmonic oscillator plus a spin-orbit interaction. A more realistic but also complicated potential is known as Wood-Saxon potential. IGAL Talmy developed a method to obtain the information from experimental data and use it to calculate and predict energies which have not been measured. This method has been successfully used by many nuclear physicists and has led to deeper understanding of nuclear structure. The theory which gives a good description of these properties was developed. This description turned out to furnish the shell model basis of the elegant and successful interacting boson model. Deformed harmonic oscillator approximated model. Consider a 3-dimensional harmonic oscillator. This would give, for example, in the first 2 levels we can imagine ourselves building a nucleus by adding protons and neutrons. These will always fill the lowest available level. Thus, the first 2 protons fill level 0, the next 6 protons fill level 1, and so on. As with electrons in the periodic table, protons in the outermost shell will be relatively loosely bound to the nucleus if there are only few protons in that shell, because they are farthest from the center of the nucleus. Therefore, nuclei which have a full outer proton shell will have a higher binding energy than other nuclei with a similar total number of protons. All this is true for neutrons as well. This means that the magic numbers are expected to be those in which all occupied shells are full. We see that for the first 2 numbers we get 2 and 8, in accord with experiment. However, the full set of magic numbers does not turn out correctly. These can be computed as follows. In a 3-dimensional harmonic oscillator, the total degeneracy at level n is, due to the spin, the degeneracy is doubled and is. Thus the magic numbers would be for all integer k. This gives the following magic numbers: 2, 8, 20, 40, 70,112, which agree with experiment only in the first 3 entries. These numbers are twice the tetrahedral numbers from the Pascal triangle. In particular, the first 6 shells are level 0, 2 states equals 2, level 1, 6 states equals 6, level 2, 2 states plus 10 states equals 12, level 3, 6 states plus 14 states equals 20, level 4, 2 states plus 10 states plus 18 states equals 30, level 5, 6 states plus 14 states plus 22 states equals 42, where for every L there are 2 L plus 1 different values of ML and 2 values of Ms, giving a total of 4 L plus 2 states for every specific level. These numbers are twice the values of triangular numbers from the Pascal triangle. 1, 3, 6, 10, 15, 21. Including a spin-orbit interaction. We next include a spin-orbit interaction. First we have to describe the system by the quantum numbers J, M, J and parity instead of L, M, L and Ms, as in the hydrogen-like atom. Since every even level includes only even values of L, it includes only states of even parity. Similarly, every odd level includes only states of odd parity. Thus we can ignore parity in counting states. The first 6 shells, described by the new quantum numbers, are level 0, 2 states, even parity, level 1, 2 states plus 4 states equals 6, odd parity, level 2, 2 states plus 4 states plus 6 states equals 12, even parity, level 3, 2 states plus 4 states plus 6 states plus 8 states equals 20, odd parity, level 4, 2 states plus 4 states plus 6 states plus 8 states plus 10 states equals 30, even parity, level 5, 2 states plus 4 states plus 6 states plus 8 states plus 10 states plus 12 states equals 42, odd parity, where for every J there are 2 J plus 1 different states from different values of Mj. Due to the spin-orbit interaction, the energies of states of the same level but with different J will no longer be identical. This is because in the original quantum numbers, when is parallel to, the interaction energy is positive, and in this case J equals L plus S equals L plus 1/2. When is anti-parallel to, the interaction energy is negative, and in this case J equals L minus S equals L minus 1/2. Furthermore, the strength of the interaction is roughly proportional to L. For example, consider the states at level 4. The 10 states with J equals 9/2 come from L equals 4 and S parallel to L. Thus they have a positive spin-orbit interaction energy. The 8 states with J equals 7/2 came from L equals 4 and S anti-parallel to L. Thus they have a negative spin-orbit interaction energy. The 6 states with J equals 5/2 came from L equals 2 and S parallel to L. Thus they have a positive spin-orbit interaction energy. However, its magnitude is half compared to the states with J equals 9/2. The 4 states with J equals 3/2 came from L equals 2 and S anti-parallel to L. Thus they have a negative spin-orbit interaction energy. However, its magnitude is half compared to the states with J equals 7/2. The 2 states with J equals 1/2 came from L equals 0 and thus have 0 spin-orbit interaction energy. Deforming the potential, the harmonic oscillator potential grows infinitely as the distance from the center R goes to infinity. A more realistic potential, such as Woods-Saxon potential, would approach a constant at this limit. One main consequence is that the average radius of nucleons' orbits would be larger in a realistic potential. This leads to a reduced term in the Laplace operator of the Hamiltonian. Another main difference is that orbits with high average radii, such as those with high n or high L, will have a lower energy than in a harmonic oscillator potential. Both effects lead to a reduction in the energy levels of high L orbits. Predicted magic numbers together with the spin-orbit interaction, and for appropriate magnitudes of both effects, one is led to the following qualitative picture. At all levels, the highest J states have their energies shifted downwards, especially for high N. This is both due to the negative spin-orbit interaction energy and to the reduction in energy resulting from deforming the potential to a more realistic one. The second to highest J states, on the contrary, have their energy shifted up by the first effect and down by the second effect, leading to a small overall shift. The shifts in the energy of the highest J states can thus bring the energy of states of one level to be closer to the energy of states of a lower level. The shells of the shell model are then no longer identical to the levels denoted by N, and the magic numbers are changed. We may then suppose that the highest J states for N equals 3 have an intermediate energy between the average energies of N equals 2 and N equals 3, and suppose that the highest J states for larger N have an energy closer to the average energy of N-1. Then we get the following shells: first shell, 2 states; second shell, 6 states; third shell, 12 states; fourth shell, 8 states; fifth shell, 22 states; sixth shell, 32 states; seventh shell, 44 states; eighth shell, 58 states, and so on. The magic numbers are then 2, 8 equals 2 plus 6, 20 equals 2 plus 6 plus 12, 28 equals 2 plus 6 plus 12 plus 8, 50 equals 2 plus 6 plus 12 plus 8 plus 22, 82 equals 2 plus 6 plus 12 plus 8 plus 22 plus 32, 126 equals 2 plus 6 plus 12 plus 8 plus 22 plus 32 plus 44, 184 equals 2 plus 6 plus 12 plus 8 plus 22 plus 32 plus 44 plus 58, and so on. This gives all the observed magic numbers, and also predicts a new one at the value of 184. Another way to predict magic numbers is by laying out the idealized filling order. For consistency, S is split into J equals 1/2 and J equals -1/2 components with 2 and 0 members respectively, taking leftmost and rightmost total counts within sequences marked bounded by P gives the magic and semi-magic numbers S, P greater than 2, 2/6, 8. So magic numbers chapter 2, 2/6, 8. D, S, F, P greater than 14, 18, 20, 20, 28, 34 to 38, 40, so 14, 20, 28, 40. G, D, S, H, F, P greater than 50, 58, 64, 68, 70, 70 80 seconds, 92,100,106,110,112, so 50, 70 82,112. I, G, D, S, J, H, F, P greater than 126,138,158,168,168,184,198,210,228,234,238,240. So 126,168, 184,240. The rightmost predicted magic numbers of each pair within the quartets bisected by a double tetrahedral numbers from the Pascal triangle. 2, 8, 20, 40, 70,112,168,240 are 2 by 1, 4, 10, 20, 35, 56, 84,120. And the leftmost members of the pairs differ from the rightmost by double triangular numbers. 2 to 2 equals 0, 8 to 6 equals 2, 20 to 14 equals 6, 40 to 28 equals 12, 70 to 50 equals 20, 112 to 82 equals 30, 168 to 126 equals 42, 240 to 184 equals 56, where 0, 2, 6, 12, 20, 30, 42, 56 are 2 by 0, 1, 3, 6, 10, 15, 21, 28. Other properties of nuclei. This model also predicts or explains with some success other properties of nuclei, in particular spin and parity of nuclei ground states, and to some extent their excited states as well. Take 1780 as an example. Its nucleus has 8 protons filling the 3 first proton shells, 8 neutrons filling the 3 first neutron shells, and 1 extra neutron. All protons in a complete proton shell have total angular momentum 0. Since their angular momenta cancel each other, the same is true for neutrons. All protons in the same level have the same parity, and since the parity of a pair of particles is the product of their parities, an even number of protons from the same level will have +1 parity. Thus, the total angular momentum of the 8 protons and the first 8 neutrons is 0, and their total parity is +1. This means that the spin of the nucleus, as well as its parity, are fully determined by that of the 9th neutron. This one is in the first state of the 4th shell, which is a d shell, and since this gives the nucleus an overall parity of +1, this 4th d shell has aj equals 5/2. Thus, the nucleus of 1780 is expected to have positive parity and total angular momentum 5/2, which indeed it has. The rules for the ordering of the nucleus shells are similar to Hund's rules of the atomic shells. However, unlike its use in atomic physics, the completion of a shell is not signified by reaching the next n. As such, the shell model cannot accurately predict the order of excited nuclei states, though it is very successful in predicting the ground states. The order of the first few terms are listed as follows: 1s, 1p 3/2, 1p 1/2, 1d 5/2, 2s, 1d 3/2. For further clarification on the notation, refer to the article on the Russell-Saunders term symbol. For nuclei farther from the magic numbers, one must add the assumption that due to the relation between the strong nuclear force and angular momentum, protons or neutrons with the same n tend to form pairs of opposite angular momenta. Therefore, a nucleus with an even number of protons and an even number of neutrons has 0 spin and positive parity. A nucleus with an even number of protons and an odd number of neutrons has the parity of the last neutron, and the spin equal to the total angular momentum of this neutron. By last, we mean the properties coming from the highest energy level. In the case of a nucleus with an odd number of protons and an odd number of neutrons, one must consider the total angular momentum and parity of both the last neutron and the last proton. The nucleus parity will be a product of theirs, while the nucleus spin will be one of the possible results of the sum of their angular momenta. The ordering of angular momentum levels within each shell is according to the principles described above, due to spin-orbit interaction, with high angular momentum states having their energies shifted downwards due to the deformation of the potential. For nucleon pairs, however, it is often energetically favorable to be at high angular momentum, even if its energy level for a single nucleon would be higher. This is due to the relation between angular momentum and the strong nuclear force. Nuclear magnetic moment is partly predicted by this simple version of the shell model. The magnetic moment is calculated through J, L and S of the last nucleon, but nuclei are not in states of well-defined L and S. Furthermore, for odd nuclei, one has to consider the 2 last nucleons, as in deuterium. Therefore, one gets several possible answers for the nuclear magnetic moment, one for each possible combined L and S state, and the real state of the nucleus is a superposition of them. Thus, the real nuclear magnetic moment is somewhere in between the possible answers. The electric dipole of a nucleus is always 0, because its ground state has a definite parity. so its matter density is always invariant under parity. This is usually the situations with the atomic electric dipole as well. Higher electric and magnetic multipole moments cannot be predicted by this simple version of the shell model, for the reasons similar to those in the case of deuterium. Alpha particle model. A model derived from the nuclear shell model is the alpha particle model developed by Henri Margenau, Edward Teller, K. Perring, Th. Skyami. Books. Talmy, IGAL, De Charlotte. Nuclear Shell Theory. Academic Press. ISBN 0-486-43933-X. Talmy, IGAL. Simple Models of Complex Nuclei. The Shell Model and the Interacting Boson Model. Harwood Academic Publishes. ISBN 3-7186-05551-1. Recent lecture. IGAL Talmy. On Single Nucleon Wave Functions. RIKEN Nishina Center. Internet streaming broadcasting both on WM and Quartet and DVD ISO delivery are now available at RIKEN Nishina Center.